what we're going to talk about today, we finished talking about, at least temporarily, about continuous time domain analysis, time domain analysis of the continuous systems. What we're going to be doing as of today, next few lectures, is time domain analysis of discrete systems. So let's look at that. So discrete, what is a discrete time signal? It's essentially a bunch of numbers that occur discrete in time. We are now restricting ourselves that the signal exists only at the given points in time. It's still, for the purpose of the analysis that we're going to be talking here, it is still analog in the y domain, right? It can take any value from a certain interval, but the signal only exists at a given instances in time. These kind of, so I would say here, sequence of numbers. How do these signals come to be? Well, they may arise naturally, right? If you look at, for example, stock market reports, they come every 15 minutes. So every 15 minutes, you get a number that tells you what the stock value is for a given company. So sometimes the signals themselves are discrete in time, but a lot of times, actually most of the time, our signals are discrete because they are a result of the sampling of the analog signals. When we process voice, when we process video, when we process pretty much every signal in the modern world, the signal goes through sampling, and then it really becomes a bunch of numbers that we now process, do the filtering or whatever is the operation that we perform. Here's the notation that we're going to use. We're going to use x of nt to indicate signal x that is sampled at the time nt. The value of that sample, we're going to just call x of nt. What you will find out is, as far as the theory of all of this is presented, as long as you're sampling with a time that is, in agreement with your Nyquist sampling criteria, then everything becomes relative to your sampling frequency. And usually, since everything scales with the sampling frequency, a lot of books, and your book is not an exception, normalize everything to t equal 1. So then you kind of talk about x of n, the nth sample, right? And you process accordingly. So here t is your sampling interval. And a lot of times I'm going to use this kind of notation to indicate the whole series of samples that are coming from this particular signal. Now, the first thing, we're going to follow very much similar approach that we did for continuous systems. First thing I have to define is something that we're going to call size of a discrete signal. We're going to define energy and power in this settings too. So let me put that as a subtitle, size of discrete time signals. Let's first look at energy. Energy of a signal, discrete time signal x of n, is going to be defined as sum when n goes from minus infinity to plus infinity, the magnitude of x of n squared. And then power, we understand power is average energy per time. Well, time here is per number of samples. So we're going to define power as a limit when n goes to infinity, 1 over 2n plus 1, sum from minus n to plus n x of n squared. Now, some of you may wonder, why do I have to take the absolute value and then square? If x of n is a real sample, I don't have to, because the square of a real number is the square of its absolute value. But if x of n is a complex number, then I have to square it first, take the magnitude first and then square it. Okay? Based on these two equations, we can, just like we did with continuous signals, we can classify discrete time signals into some broad categories. So we can say if energy is finite, therefore power is 0, the signal is an energy signal. Right? If energy is infinite, power is finite, then we're talking about power signal. Now, just like I said in the continuous case, signal does not have to belong to any one of these categories. We're going to look at the signals that can be for which energy is infinite and, for example, power is infinite. But those signals are rare in practical applications. Practical applications, your signals are going to be either energy signals or power signals. And usually power signals result from processes that are kind of continuous in nature and go for a very long time. And energy signals result from processes that give you bursts of energy. For example, if you're signaling in the digital communication, then when you look at your signal across one symbol, then you talk about energy signal. And when you talk about, for example, noise is a typical example of a power signal because it exists for a very long time. Let's look at an example to illustrate these definitions. This is the example 3.1 from your textbook. It says, consider a signal and the signal is x of n given as n when n is equal to 0, 1, all the way to 5. And it is equal to 0 outside. So I can say that x of n is equal to 0 when outside. So the question here is find the power, find the energy of x, and it says find the power of y, where y is periodic extension of x. So let's first find the energy of x. How does this is part A and B of part B. So part A, how does the x look like? Where here's the sampling axis n, and x of n exists for 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So these are the samples of x of n. And then outside of this range, it is equal to 0. So this is your x of n, and the unit here is 1 and 1. So how do we calculate energy? Energy is equal to sum. Well, by definition, n goes from minus infinity to plus infinity. X of n magnitude squared. But in this case, there is no need to sum anything before 0 or after 5. So this goes sum when n goes from 0, or I should really sum from 1 to 5, then n squared, right? And there is a, I'm just going to write it, 1 squared plus 2 squared plus and so on, plus 5 squared. When you add this together, that's why you should always check my notes. It says here 5, but that's not the correct result. So let me actually give you formula and then we'll fill in the blank here. The formula that you should know is this one, 1 plus 1 squared plus 2 squared plus n squared. Sum of the first n numbers, square of the sum of the first n numbers is equal to n plus 1, 2n plus 1 over 6. That's one of these formulas. They're very easy to prove there. You use mathematical induction to prove these formulas. So if I now plug in, this is sum from 1 to 5, so this becomes 5 times 6 times 11 divided by 6, so it ends up being 55. So the proper answer here is 55. I guess I just forgot 1 5. Another formula that we maybe don't need it here, but we can use it somewhere else. The sum of the cubes, so it's 1 cubed plus 2 cubed plus all the way to n cubed. And this gives us formula n squared, n plus 1 squared over 4. So these are two formulas you may keep handy because they help in the various process. But the energy is straightforward. In a discrete, in a continuous time signals, it was the area under the curve, closest approximation to, or closest relative to the area under the curve is the sum of the squares of the amplitude of the samples, right? And this is how we define the energy in the discrete time case. Now, let's look at part B. Part B says, well, create a periodic extension of x of n and calculate its power. 5, so this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5. So, so this is 6, that's 7, 8, 9, 10, 11, and so on. So here's the first period. And 5 is equal to 5, and then it collapses again. So 1, 2, 3, 4, 5. So you get a signal that looks like this. It's a periodic signal, y of n. So the question is, first, what is the energy of y? It's a sum of y of n, magnitude squared, when n goes from minus infinity to plus infinity. So what is the value of this summation?
Infinity.
It's infinity, right? Right, because this goes without bounds. So if you keep on adding them, it will always be larger and larger. The power of y, definition is limit when n goes to infinity, 1 over 2n plus 1, sum from minus n to plus n, y of n magnitude squared. But since this is a periodic signal, I don't have to integrate over entire n axis, right? All I need to do is integrate within one period, because I know that everything repeats from period to period. So, and then divide by the actually length of the period. So it becomes 1 over 6 sum from 0 to 5 n squared, right? Because that's a value of the function of y of n for over this first period. So this becomes 1 over 6 times, I guess I could use this formula here, or I already sum it, so times 55. So it's 55 over 6 is the power of y of n. X of n is the energy signal, y of n is a power signal. So we put it here as a note, X of n, energy signal. And y of n is a power signal.
Can you explain how you skipped
All you
one?
can
This signal. I know it's supposed to.
How did it skip one?
No, the signal. How you went from number 1 to the 5th sample, and then it dies down, and then
Okay.
going up again.
So, y is the periodic extension of x. So how do I do that? Well, I take how many samples are in x? Non-zero, the samples that I know. It starts from 0 to 5, right? So you take this, put it here, and then you put it here, put it here. You know, you're performing the periodic extension. Now the question is, why is here a 0, right? Because there was a 0 here,
Okay.
right? So you go to 11, and then 12 is also going to be 0, right? Just like minus 6 was 0.
Sir, I'm confused with 1 over 2n plus 1.
Yeah.
Can we just take it as a period if we know that it's not going to negate?
Yeah, you take with only one period. I could have been, the thing is I need to integrate from over one period, right? So I can choose to integrate whatever period I want, and I just chose to integrate from 0 to 5, and the length of that period is 6. Right, so
Because if we
6
substitute,
samples, right?
if we substitute n equal to 5 in that equation, then it will be 1 by 11 summation of.
Yeah, but why
but
would
it's
you?
minus n to n.
Yeah, why would you do that? You don't,
Yeah, right.
you don't substitute stuff without thinking. What this is just a, remember, this whole thing that I have here is not what it looks like, right? You're never gonna be doing this sum, or rarely you're gonna be doing this sum. It's my way to say power is average energy per time, or per number of samples. Just like in the continuous time domain, we had a limit to, when t goes to infinity, 1 over t integral dt. This whole thing is a symbolic, representation of averaging over time. Right? And this is averaging over samples, right? Don't take it literally. Just understand what the physical meaning of it is. And then once you understand physical meaning, you calculate it in a way that is convenient, right?
So again, there is confusion. If we take summation minus n to n, then summation minus n to n can be 2 times summation 0 to n.
No, it's because you forget the 0 sample, right? It's not. You're double booking, right? You're saying summation from 1 minus n to n is 2 times 0 to n. But you are counting sample at 0 twice.
2 plus 1 times 0 to n.
Yeah, so be careful. Go ahead.
But the sample at 0 doesn't contribute, right? It's 0.
In this case, it does. In this case, the sample of 0 doesn't contribute, but in other cases, it will.
0, 1, 2, 3, 4.
Yeah, but 2n plus 1 equals 6.
Okay.
You say that 2n plus 1 equals to 6. It means that you do not count it in 0.
No, you gotta ask questions here, because this 2n, this 6 here is
It's a
not
period,
5
right?
minus 0. It
No.
is the number of samples in a period.
Yeah.
So how many samples are in a period? How many samples are in a period? 6 samples. So that's so you accumulate this much energy over 6 samples. So average energy per sample is what we are after, right? And here I have a period of 6 samples. So 0, 1, 2, 3, 4, 5. So those are 6 samples. I accumulate 55 energy divided by 6 samples. Right? So it's not 5 minus 1, it's count, you count the samples, right?
Yeah, you need to count the zero, right?
Yeah, you count 0 to, because I could have started from 2 to 8. That's also a period, right?
Right.
Don't let 0 confuse you, right? All right. So just like in the case of the continuous time, we have some common operations that we're doing. I'm not going to go through all of them. They're trivial extensions of what we did with continuous signals. But let me point out some subtle differences where appropriate. So, useful signal operations. Shifting, time reversal, downsampling, or sometimes referred to as decimation, upsampling, or sometimes referred to as interpolation. Okay? So let's go through some of them. First one, shifting. Since the signal is discrete here, shifts have to be discrete as well, right? And the shifts are in integer number of samples. So if x of n is discrete time signal, then x of n minus n0 is shifted to the right, right? If we assume that on the x-axis is some notion of time, and we say that this is delayed by n0 samples. Likewise, x of n plus n0 is shifted to the left. Or advanced. By n0 samples. The second one was a time reversal. If we have x of n as a discrete time signal, then xr of n, which is x of minus n, is the time reversal, right? Really nothing more to be said here. It's exactly the same notion as we have for continuous signals. Let's take a look at downsampling and upsampling. Downsampling and upsampling are equivalent to your scaling in a time domain, but there are in a continuous time signals, but there are some subtle differences. So let's just go through them. First, downsampling. If x of n is your discrete time signal, then xd of n, d stands for decimated version of the x of n, is essentially x m times n. So decimation means that you're not picking every sample of x of n, but you're picking every nth sample, right? So you're skipping n minus 1 sample and picking up every other sample. So let's draw these two signals. Let's say this is your original signal. Let's say 0, 1, 2, 3, 4. And let me just draw, although, so these are your samples. Now, this is your x of n. xd of n. Let's say n is equal to 2, just for the case of this example. So it is really not every other sample of this. It's the every other sample of this, but ticking at the clock of increments of n. So if you look at now, how does xd of n look like? I'm going to have 0, 1, 2, 3, 4. And I'm going to pick 0 sample here. Then I'm going to pick sample number 2 to be at time n equal 1. Then I'm going to pick sample number 4 to be at the time 2. Pick sample number 6 to be at the time 3. And then pick sample number 8 to be at the time 4. Right? So you see what is happening, you know, just like we had in the case of the continuous time signal, there's a shrinking in time. This signal here, xd of n, moves faster than the signal x of n, right? It kind of goes to the values faster than the other one. Now you're skipping some samples in the process, but so the transformation is somewhat irreversible, right? If you know this one, you know this guy, but if you know this one, only under certain conditions you can reconstruct the original one, because you're missing some of the samples. Every other sample is gone from this one here. Okay?
So what about the power of two signals?
There's nothing to say beyond what I just said here. You would take the sum of the square of the samples and calculate. And the chances are they're going to be different. Right?
I got a question. Can we generate a signal like x of n, y of n? Can we generate in reality?
Can you generate these signals in reality?
Yes. If we can't, why we need to take in our analysis?
Okay. The first thing is, can you generate this signal in reality? It's a basically sawtooth signal. It is present in every one of your scopes, right? It is the signal that exists all the time, right? We have the signals quite often. So the question is, can we generate it? You can generate it easily in software. You can generate it in hardware. It's very easy to generate. Now, back to your other question, is if we cannot generate it, why do we still analyze? Well, delta pulse, we could not generate either, but you saw how useful it was in our understanding of how the system works. A lot of time, we actually work with the stuff that we cannot generate, but it's useful for us analytically to explain things. The typical example is, every time we do the Fourier transform, you integrate from 0 to infinity. Now, does infinity exist? Not in, physically we have a problem with it, but mathematically we don't, right? We know what we mean, right? The infinity is on the other side of 0, right? Mathematically, right? So it's fine, right? And it's helpful for us to, formulate certain things and do our math in a more elegant way. So we have motivation to even work with the things that you cannot generate physically, but they help us do certain things. Just like, and I say this a lot of times in our communication theory and other courses that we over time we develop this toolbox of different mathematical views that we're going to go to when trying to explain certain things. And the most common is our Fourier analysis toolbox, where when I look at the signals, I really don't see signal itself, but I see a whole bunch of sinusoidals that align themselves in a very special way to form this signal, right? That doesn't happen, right? Nobody aligns those sinusoidals to form the square wave, right? But it's very useful for me to see it that way, because now if I decompose this square wave into a bunch of sinusoidals, and I put a filter in front of it, it is straightforward for me to understand what comes out at the output of the filter, right? Because this filter is going to let some sinusoidals go through, change their magnitudes and phases, and completely eliminate other sinusoidals. So by seeing it that way, I can effectively calculate what comes at the output, right? So a lot of times, you know, we have very strong motivation to deal with things that we cannot really create, basically. Right. Any other comments about this? Just going back to his comment, how about the power of these two? Well, the power is going to be different, and probably you can relate it somehow. And you know, if I'm given the actual form of x of n, then you can plug this in these two equations and calculate the power in one case or the other case. So this is upsampling. Sorry, downsampling. Let's look at what happens when you're upsampling. It's even more interesting than downsampling. So this is for upsampling or interpolation. So we start with x of n, which is a discrete time signal. And we create, how do I interpolate the signal x e of n, interpolated signal. And interpolation is performed in two steps. First, you have to let me actually go through, let me put it here, step one. Is expansion of x of n. Expansion. The step two would be interpolation of values in between samples of x of n. Let me give you an example here, and then we'll discuss, because here the situation is not necessarily unique. Let's say this is your original signal, x of n. Let's say it looks somewhat like this. I'm drawing it relatively simple so that I can replicate it, downstairs with an ease. Okay, so this is my x of n. These are the n's, 0, 1, 2, 3, 4. So after step one, here's what I have. 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. So this is so this sample is the same. Now at the point 1, I don't have a sample. At point 2, I'm going to have x of 1. So this is this guy here. Then at, so this is 1, 2, 3, 4, 5, 6, 7, 8. The next sample is here at 4. The next sample is at 6. The next sample is at 8. So this is how expanded version of n look like. Now the question is, I don't have the values at these points. So That's where the second step is. And the question is, how do you populate these values? There is not a unique way of doing that. And when we say upsampling, we also have to say how you're going to populate the values in between. One of the most common ways is just to leave them zeros, right? This is frequently done in multi-rate signal processing because you're actually just adjusting the rate of the two signals. If this is in the final stage when you're trying to, let's say, pass this signal to some digital to analog converter, then one of the common ways of getting the values in between is to do something like this, right? So that's a interpolation step. What did I do here? I have done the linear interpolation between these samples. How do you actually do interpolation? Will be a function of what is actually being done in a particular example. There are, as I said, there is no unique way of doing this. You can interpolate linearly, you can interpolate what you call just hold this value until the new one comes, or you can do sync interpolation, or do many, many different ways of interpolating, and that's going to depend on application. What I have shown here is both in this case and this case is processing by factor of 2. What I did here is downsampling or decimation by factor of 2. Here I did upsampling or interpolation by a factor of 2. 2 is just for illustrative purposes. You can do with other factors. Commonly, you find, because of just the way how we do arithmetic in computers, commonly you find that these factors are going to be factor of 2, 4, 8, 16 powers of 2. But it doesn't have to be, and there are some signal processing algorithms that use different factors. Any questions about this?
Is it supposed to be x of e 1 over m times n?
Is equal x of n over, right? This is still of n, right? Because it's still having a value at the same increments of n as this one. But xe of n is equal n over n for this for the samples where this ratio is integer, and then we decide what happens for the samples in between.
Well, I guess what I was asking is over here we had m equals 2. So x equals 2n.
M, sorry, M. Yeah.
Okay.
I'm sorry. Yeah, M factor. But be aware, this is just a notation, right? We have to know what we mean by this, because when n is equal to 1, this makes no sense. You have no sample at 0.5, right? This is only true when this is an integer, right? So when n is equal to 2, this is equal to x of 1. But when n is equal to 3, then I have to decide how I interpolate for that point, because it makes no, because this is not an integer, right?
And there's no indication of the interpolation method in the naming of that signal, x of n over n?
This is something that needs to be known. It needs to be supplied outside. I mean, a lot of times it would make, it would be obvious what needs to be from a given scenario. Okay, just like in the case continuous time, let me introduce some useful signals that we're going to be working with here. Some useful discrete time signals. So discrete discrete time impulse. The notation is delta of n, and this one is equal to 1 when n is equal to 0, and 0 when n is different than 0. Okay? Graphically, how does this one look like? This is your n-axis. These are all the other samples. All right, so this is delta of n. One thing that you should notice right away is this is a very nice function of the sample. There's no weirdness that we had associated with delta of t. Because remember, delta of t used to go to infinity, but it exists only in one point, and the area under the curve was finite and equal to 1. So that was a definitely mathematical construction that we had to deal with over there. Here, this signal is very, very much down-to-earth real signal. It is 0 everywhere except point n, where n equals 0, where it's equal to 1. Right? So it's a very, very nice behaving signal. The second one is discrete time step function. Also, I think we're going to call this one u. U of n is equal to 1 when n is greater or equal to 0, 0 when n is smaller than 0. Again, very similar shape to the one that we had for continuous time. This is 0, 1, 2, 3, 4, and so on. 1, 2, 20. Okay, so let's take a look at the third one. So this is discrete time exponential. And here, x of n is going to be equal gamma to some gamma to n, where gamma is a constant. Potentially complex constant, but still a constant. So we have obviously we can see that the gamma has the magnitude that is greater than 1. X of n increases. Becomes larger over time. If gamma is smaller than 1, then x of n decreases over time or becomes smaller over time. Now, what happens when gamma is equal to 1? Well, the magnitude of it stays the same. It may alternate, or but it will stay always on the same unit circle. So it maintains its magnitude over time. This one is going to be very important to us when we start solving the difference equations. You will see that gamma to the n plays the same role in discrete systems as e to the rt played in the continuous time systems. So by using this one, we're going to be able to formulate the same stuff as we did in the continuous time characteristic equation, characteristic polynomial, roots, and so on. So the story is going to be very similar. The fourth function that we're going to use quite a bit is x of n is equal to c cosine omega n plus theta. This is I guess just a discrete time sinusoidal. discrete time sinusoidal. And find like this x of n is going to be c cosine of your omega times n plus theta. Or a lot of times we're going to say that this is c cosine 2 pi dash n plus theta. With obvious definitions here. C is the magnitude, theta is the phase, omega here is the angular frequency, and 2 pi f is f is here is the frequency, but frequency is expressed in number of samples per 2 pi, right? So here when I talk about frequencies, I'm going to say it's 10 samples per full period, because there is really no notion of time here. We're normalizing everything to the sample interval. And then I think the last one that we're going to introduce here as a useful function is going to be your complex sinusoidal. Complex sinusoidal. And here x of n ends up being some constant e to the j omega times n. And as we know, we can say that this is cosine n plus j sine omega n. Because the Euler's rule still holds here. Okay, so those are some useful functions that we're gonna be encountering as we do the analysis. Go ahead.
So can we say like exponential when mod of gamma equal to 1 is a function of u of n plus u of minus n?
Which one?
The third case of exponential function, their mod of gamma equal to 1, magnitude of gamma is 1, the third case.
This one.
Yeah, third case of the third, yeah. So can we say that as an u of n plus u of minus n?
No, because let me give you, this is what he's saying. Let's say gamma to the n, we're looking at this function here, and with this condition, right? And let's call this x of n. And you're saying, can I say that x of n, in this case, is u of n plus u of minus n? And in other words, here's what you're saying. You're saying that if I have, first of all, how does u of n plus u of minus n look like? It is equal to 1 here, 1 here, 1 here, and so on. It is equal to 1 here, 1 here, 1 here. What's the value at this point? 2, 2, right?
Oh.
So, but that's not, I just wanted to point out that from this definition here, right? But that's not even significant in this case. Let me put gamma that fits this description. Let's say gamma is equal to e to the j pi. So what's the magnitude of gamma? It is equal to, e is equal to 1, right? But how does this sequence look like? Well, the sequence looks like e to the j phi, e to the j 2 phi, e to the j 3 phi, and so on, right? 1 e to the minus j phi, and so on, right? So you see that this is definitely different than this, right? This is just a special case when phi is equal to 0, right? Then you get what you thought by this, right? Maybe minus delta n, right? That's what you had in mind, right?
Yes.
But if just this condition is imposed, then you can actually be on a unit circle, right?
That I didn't understand.
Yeah. So that's what it's what we are after here, and this is a very important case for us because at some point this phi is going to become omega n. And we're going to be doing DFT and FFT and all of these kind of things, right? So this is what we have in mind when we set gamma equal to 1 by magnitude. Okay? So let's take a look at some examples of discrete time systems. Of discrete time systems. And in this case, since we're not going to be doing any difference equations, we're going to stay away still from a general discrete time system. We're going to look at a couple of simplest ones, right? We're going to look at digital differentiator and digital integrator, and they're just about the simplest digital systems. But I want you to kind of get a feel of how we think in digital and how it relates to the analog counterpart. So let's first look at digital differentiator. What is the role of this system? You put in a signal, and what you get at the output, you get a derivative of that signal. So it's supposed to perform the operation of a differentiation, but it's supposed to do that in a digital domain. So first thing we do is we consider, I guess here, y of t as dx of t over t. And we remember that really this is limit when t goes to 0, 1 over t, x of nt minus x of n minus 1 t. Let me divided by, I guess this is it. Right? So how do we take the derivative? We said that increment is smaller than, as t goes to 0, it's the difference between two adjacent values of the function. Now, we can now say y of n is the limit when t goes to 0, 1 over t, x of n minus x of n minus 1. Right? This is what we would like to come at the output of this system. You have two adjacent samples, n and n minus 1, two adjacent values. You take the difference, divide by t, and you get the value of y of n. If t is selected to be small, if t is small, then y of n is approximately 1 over t x of n minus x of n minus 1, just this way. Now, let me ask you this. When you look at these two, then you say, okay, what's the big deal? What's the difference between these two, right? How is this different? It seems like I just dropped this, and I said, well, this is the same as this. What we are doing when we neglect, when we just drop this out, is we're neglecting the higher order terms of the Taylor's expansion, right? Remember, x of sample of x of in any point is x at that point. Let me just write it here. X at any point t0, or let me just say x of t around the point t0 is x of t0 plus x prime at t0, t minus t0 plus x double prime at t0 over 2 factorial, t minus t0 squared, and so on, right? So that's how I can approximate function at any point t0, the value of that function plus the first order term. Now, if I neglect these two, then you can see that this becomes, then I'm really, you know, and I substitute the samples in this thing, in these two, then you actually end up with this term coming out, and you can try it. But what I'm doing here is we have to make sure that the t is small enough so that all of these higher order terms can be neglected. And there's some math that goes in here, and the analysis that leads to the bound on how small this t needs to be. And it turns out you're okay, this approximation is valid if t is smaller than 1/2f max, right? Which is not a surprising result. This f max is the maximum frequency in the spectrum of x of t. This is yet another straight forward consequence of your sampling theory.
So it should be less than half of the maximum time limit. 1 by x will be Tmax. So
Should be
Tmax
less
by
than,
2.
should be less than what?
Tmax, half of the Tmax.
Half of the f, yeah. This
1
is
by
the
f max
maximum.
will be Tmax, so
So 1/2 of that, right? Half of the, half, the 1/f, 2f max is the sampling frequency, right?
sir, is it going somewhere in Nyquist rate or something?
Yeah, yeah, this is related to Nyquist. Nyquist sampling rate is 1/2f max.
Yeah.
Right, so if your t is smaller than that, then this approximation can be taken to hold. Now, how would this system look like if you were to form this digital differentiator? This is the block diagram. We would have some way of transitioning from continuous to digital domain. Usually some sort of your A to B converter. So here is your x of n. You would just delay this one by 1n, and you would plus minus, and then you would scale this with 1/2. And this is where you get your y n, and then you can do digital to continuous to get your y of t. So that's a way how you can implement digital differentiator. This is how we do a lot of our processing these days. You have your input and output, which are usually very often some sort of analog signal that you're processing, your voice, your image, your all sorts of measurements coming from sensors are usually coming as analog signals, some voltages, currents, whatever it happens to be particular quantity. Then if you need to process it, we kind of pair it with these two blocks that transition between analog and digital world, and then we do all the processing inside. And the processing is just manipulation of some numbers, executing some sort of equations. Okay, so that's an example of a digital system. We will later see the difference equation associated with this one, but that's how one of the simplest digital systems. Let's take a look at yet another one. This is the digital integrator. And digital integrator needs to do a kind of process that is inverse of the digital differentiator. You would feel you would, let's say, put in a signal x of t, and what you get out is the primitive function, the function that whose derivative is equal to the x of t. So if you look at, let's do our, again, by looking first what happens in the time domain. This is x of t, and then this area under the curve is gonna be your y of t. That's I guess, continuous time. That's t. Discrete time equivalent can be seen like this. This is your n. X of n is now discrete values here. So this is x of n. And what is y of n? Y of n is going to be these areas m together. So these areas here are going to be y of n. And you can see as t approaches 0, these two pictures start to look very much like one another because you're sampling almost continuously and you're integrating accordingly. So you're calculating the entire area under the curve. So if I write it from here, so this is discrete time. I can say y of t is integral from minus infinity to t, x of tau d tau. That's what continuous time integration do. Here in a discrete domain, you can say y of nt is going to be limit when t goes to 0, sum when k goes from minus infinity to n, x of kt times t, right? Because the area of this I guess polygon or this rectangle is x of kt height times t of width. Or if we normalize everything to based on t, you can say y of n is limit when t goes to 0, t times sum k goes from minus infinity to n x of n. So this is how we would perform integration. I just noticed here in notes it says t goes to infinity. Yeah, that's a typo. It should go t goes to 0, right? So it should be 0 here and 0 here, not what we have in notes. Now, if t is small enough, so the same argument that we had over there for differentiation hold. So for small t, we can have y of n is equal to t times sum k goes from minus infinity to n x of n, right? But this I can rewrite slightly differently. I can say this is t. Let me just do it this way. Sum k goes from minus infinity to n minus 1 x of n, and then plus t times x of n. What did I do? I have split this summation to sum from minus infinity to n minus 1, and then the last term here is going to be t times x of n. Really, this should be k. I apologize. This is k, and I probably made it. No, I didn't make that mistake.
Okay.
Oh, I didn't make it here, right? So the summation is over k. So here I'm saying for small t, I can drop this limit here. And then I take this summation and I separate it in two pieces. One is summing up to n minus 1, and the other one is summing the last x of n. Well, let me ask you this. What is this? It's a sum. Let's say this is here n. What this is sum of all of these up to this point. So what is that value? That's the value of y at the previous sample, right? At n minus 1, I would be summing only up to this point, right? So what you have here is your y of n minus 1. Now if I rewrite this, I can say that y of n minus 1 divided by t is equal to x of n. And then you can see right away that this is completely dual system to the differentiator, as we kind of expected, because what happened here is the input and output change places. So here, if the derivative of the output is actually input, so that means that the output is the integral of the input. Now, what you should notice from these two simple examples, that what we ended up in both cases are these equations that relate present and past samples of the input to the present and past samples of the output. And these are two rudimentary systems, so we don't have, in this case, we have only the present value of the input and present and past value of the output. We have the other way around over there. But in general, for any discrete systems, this is how we're going to be able to describe these systems. We're going to be able to describe them as linear relationships between present and past values of the input and present and past values of the output. These kind of equations we're going to call difference equations. And just like differential equations describe the time domain continuous systems, these kind of equations are going to be used to describe discrete time systems. So we're going to be working with them. Now, the last thing that I want to mention today is classification of the discrete time system. And I'm just going to list it here. And there's really nothing much to be said there beyond what we have already discussed for continuous time. So the extension is pretty much straightforward. So classification of discrete time systems. These systems can be linear, non-linear. How would you extend the definition? When is the discrete time system linear? Well, what is our test for linearity? Superposition, right? So if I have a discrete time system and I present two inputs or a linear combination of the two inputs, the output needs to be a linear combination of the outputs to those two inputs, right? So that's our test. If that test holds, the system is linear. If it doesn't, it's non-linear. Then we have time invariant or variant. Okay? If the system, if I take an input and I present it and I get an output and I delay that input, the output should be delayed version of the output, right? So that means no matter when I present, the same input is always going to be the same output. The system does not change over time, right? That's very much the same definition as we have for continuous case. Then it can be causal, non-causal, or memoryless, or with memory, and so on. There are all of these translate, in the same way as they did in the continuous time. So let me give you some problems that exercise this material here. There are 3.1-1-2-3-4, 3.2-1-4, 2 and dash 4, 3.3-3-4 and dash 5, 3.4-1-2 and dash 5. Right, so these are all very, very short, simple problems. that this kind of go over the material that I covered today. What we're gonna go over next time is we kind of played along, introduce some basic concepts here. We're gonna go next time and put the difference equation, say this is the equation that describes discrete time system, and then we're gonna work towards a solution, and we're gonna approach pretty much the same way. We're gonna split it into homogeneous part, or essentially zero input response, and then we're gonna calculate zero state response and put them all together. It's going to be very similar, and a lot of books actually present it side by side, but I prefer the book that is the approach that is in your book, where they are, one after the other, because they are not the same, and there are some significant differences between them. So we're going to talk about that next time.